You've probably noticed that I've gotten pretty obsessed by Venus in the last few months, and there's a bunch of reasons. There's some interesting missions that are going. There's some interesting research that's been done, but I think I need to put a lot of this responsibility into the hands of my friend Dr. Paul Byrne. He is a planetary scientist, geologist, has produced tons of really interesting research about Venus, but also is just a great evangelizer of Venus and planetary exploration in general, quite active on Twitter and other places in social media. And so I had a chance to sit down with him and talk about the current research, the status of Venus, why it's so interesting both as a world here in the solar system, but also as an analog, as an exoplanet. We talk about the recent map that he and his graduate student worked on that found 85,000 volcanoes on Venus, the potential for new active volcanism on Venus, and what the future holds for the exploration of Venus. So if you want to take your interest in Venus to the next level and turn into complete obsession, I think you'll really enjoy this interview with Dr. Paul Byrne. All right. Here's the interview. Yeah, I've gone on record a few times saying that Venus is so awful that we should just push it into the sun. And I would like to credit you, Paul, for talking me out of it, at least a little bit, a stay of execution, perhaps. You are fascinated with this world. What do you love so much about Venus? Why? What's the interest?
Okay, well, first off, I'm glad that I've done something to try and forestall its eventual demise and being tossed into the sun. That's good. I think there's two things to it, right? The first thing, and it's the thing that it drew me to Venus first, is its underdog status. Venus was the poster child for places that we went to in the 60s and 70s. And in fact, up until really the middle of the 70s, most stuff went to Venus. And that was the golden age of Venus exploration. And we learned about what the surface was like. We even saw photos of the surface. And it was all really capped off in the late 80s and the early 1990s by NASA's Magellan mission, which was the first mission and so far only mission to take global radar data of the entire surface. You need radar to see the surface. You can't photograph it through the thick clouds. And so Venus for a long time got all the attention, but that kind of went away in the mid-90s. And at that point, Mars became ascendant. And then we've now had at least 3 decades of unbroken exploration, serial exploration to the red planet. So when I started thinking about Venus in around 2016, not that long ago, and I, full disclosure, cut my teeth on Mars. I studied Mars on my PhD, and then I worked on the Messenger mission to Mercury. So I hadn't paid much attention to Venus. But as I began to kind of learn a little bit about it, and I realized it's got a lot of interesting stuff. The modern Venus has interesting stuff that we don't know much about. I was kind of horrified by how little attention had been paid to the planet since the early 90s. So its underdog status is definitely something that played a role. As I learned more about it, though, I stood back and I was like, hang on, there are some really profoundly important questions that Venus offers us the opportunity to answer. Why the hell aren't we exploring this place? And those questions, there's myriad of them. But one of the most important things, and the way I frame it to people is this: Venus is the only other Earth-sized world we will likely ever visit. We are discovering more of these so-called Earth-sized worlds. I should point out it's not Earth-like. And actually, we haven't discovered an Earth-like world anywhere in the cosmos yet, but we have discovered Earth-sized worlds. Now, Venus and Earth are almost the same size, which means you might as well say we've discovered loads of Venus-sized worlds. But the bottom line is that Earth seems to have remained habitable for pretty much its entire life, almost going right back to the oldest bits of minerals from the oldest traces of rock we can find. It looks like Earth had liquid water on the surface. And Venus doesn't.
Right.
And it may never have, or it potentially did have oceans until maybe not that long ago. We don't know. But figuring out why seems to me to be a pretty important question if we want to understand things like what governs the habitability of a large rocky planet generally, like our own. And Venus is the place. You cannot answer that question at Mars. It's too small. Mm-hmm. You certainly can't answer that question at the icy satellites. They're too small and they've got different processes going on. But in terms of understanding how do you end up with either a Venus or an Earth, that's a pretty important question in my view. And Venus is the way we get to understand the answer to that question.
I mean, for me, I think the excitement came with the rise of exoplanet astronomy. As astronomers are looking out across the cosmos, they're looking for other Earth-sized worlds orbiting around sun-like stars. And we've got one right next door.
Literally. And it's closer, by the way, And you can get there faster and more frequently than Mars, but never mind that.
Well, we'll get on to all that. And so when you realize just the cosmic lottery that we ended up with an analog to Earth that is roughly the same size, same mass, and it's right next door, suddenly all of these questions that you have about exoplanets can be played out in almost real time in a way in our solar system that was never possible. All right. Now, but let's go back to you mentioned there's a whole bunch of really interesting scientific questions that we have about Venus, not related even to its exoplanet-ness.
Right.
So what are the big questions that are currently fascinating about Venus?
Okay, I'm going to just pick a handful out of the air because there's lots of them. And to the credit of the Venus community, going back several decades now, we actually have very well-defined, exhaustive lists of questions and how we would tackle them. But one of the things, for example, is we don't know what the rocks are made of. It seems like a pretty basic thing. What's it made of? Don't know what the interior is like. We don't know how active it is. We don't know how it gets its global cloud layer, which shouldn't, we think, hang around all that long. We think that the global layer of sulfuric acid clouds would get broken down by sunlight on geological timescales. So either the layer is relatively recent, which doesn't seem particularly scientifically satisfying, or it's replenished by something. And the two things you need to replenish sulfuric acid clouds are SO2 and H2O, and those things come out of volcanoes. So it seems difficult to escape the fact that it's active, but until recently we had no evidence, no direct specific evidence we can point to. Now we have one data point. Is it active? What's it made of? What's the interior like? How come it doesn't have a magnetic field that it generates itself? Why does the atmosphere take about 7 days to go around its own axis, but the planet takes 243 days to go around its own axis? How is it that you can make some terrains on the surface look exactly like stuff on ancient parts of Earth, and yet have some places that are brand new? How come there's so few craters? There's fewer than 1,000 craters on Venus. That's kind of weird. Basic questions tied to just what it is and what it's doing. Completely, I mean, it's not impossible, I should say, to completely separate that from its, not necessarily the exoplanet angle, but simply the whole idea of planetary habitability. But even if you just weren't interested for some reason, you were an odd person, you didn't care about the history of Venus, just understanding what it's doing today, pretty basic stuff. We know what Mercury's made of because we've sent spacecraft there. We can measure the surface properties. We know what the Moon's made of because we've sent spacecraft there, measure surface properties, and we brought some stuff home. We now have a pretty good sense of what the surface of Mars is like, and we are working to bring bits home. We know what Earth is made of. We know that there is a huge amount to be gained by understanding these different bits of chemistry because they tell you all kinds of things. How planets form, what the protoplanetary disk is like, how close or not the planets are to the star they form in. Of course, that has exoplanetary bearings. But some really basic stuff that we just do not understand about Venus. Real simple stuff.
And so, put that into context. Like right now, there is a fleet of spacecraft at Mars crawling its surface, scooping through the regolith, orbiting the planet from many different nations. And there's one Japanese probe was recently at Venus. I'm trying to think, like, who's at Venus right now?
Well, so we have a Japanese probe at Venus right now, the Akatsuki probe, and it's been there since 2015, and it's telling us useful stuff about the clouds. Prior to that, we had the Venus Express, which was another orbiter that the European Space Agency had, which is the twin to the Mars Express spacecraft still operating at Mars. Venus Express and Akatsuki were largely focused on the atmosphere. So the last time we had a mission that was focused explicitly on the surface was Magellan, which ended in 1994, coming up on the 3 decades anniversary of the end of that mission. And to your point, we have lots of stuff crawling all over Mars, flying all over, literally flying on Mars, flying around Mars. But the big reason for that, well, there's a couple of reasons. And one of the reasons is that Mars is easy. At least relatively speaking, Mars is not easy. It is not easy to get to Mars. Historically, about 1 in 2 missions attempted to get there didn't, because navigating in deep space is difficult. But in the modern era, we've had a lot of stuff at Mars, and there's a couple of reasons. You can have something that will survive on the surface for, as we've seen with the Mars exploration rovers, over a decade. You can image the surface from space. That's also very helpful. It is relatively easy to get to compared with, say, outer planets destinations or Mercury. Mercury is extremely difficult to get to by virtue of the fact that it is so deep in the sun's gravity well. It actually takes a long time to get there. You've got to do a lot of flybys to slow yourself down. There was a study that was issued very late in the 1960s, early in the era of human space exploration in the United States, by the Committee on Planetary and Lunar Exploration, the complex reports. And these reports essentially were the perhaps grandparent of the modern decadal survey paradigm we have. And Complex, in one of their early reports, acknowledged that the scientific merit and interest of Mercury, Venus, and Mars is probably about the same, but that Mars is always going to be the world that's easier to do because of the conditions at Venus and the difficulty in getting to Mercury. So a lot of it is, and when I say relative ease, that's not to say that Mars is easy, but it is not as technically challenging to get there. And missions beget missions. And we're seeing that even now. There's talk of NASA developing new Mars helicopter concepts that are larger. The Mars Science helicopter concept. They're going to do 2 more helicopters flying on the next part of the Mars sample return trifecta. Every time a mission goes to Mars, it generates interest by people. Graduate students are trained, brought on board, postdoc fellows, and the community grows. And we're starting to see that with Venus, but it does mean that there's been a sustained interest in Mars exploration over the last 3 decades. And once that inertia is overcome, it's relatively easy to maintain. So a whole pile of things have factored into the fact that we've had all this focus on Mars the last 30 years and virtually no focus on Venus except for 2 spacecraft this century and no direct focus by NASA.
There have been a string of proposals, science papers, articles in Acta Astronautica about ideas for missions that could go to Venus. Like one of my favorites was sending a Stirling engine down to the surface of Venus to try and last a couple of weeks before the heat comes in. Obviously, we saw what happened with the Soviet era Venera program. They put a lot of energy into getting something to survive down on the surface of Venus. So there have been a lot of ideas. I would guess we could look through literature and find hundreds of proposals for sending missions to Venus. None flew.
Right.
Why?
I'm going to go and just stick my head out the window and start screaming for 30 seconds because
all right.
it's a question, and then I'll come back.
Come on back.
Okay,
yeah.
So the shorter answer is we're back. Thank you. Okay, I needed that. Yeah. So the shorter answer is I have no idea why. The longer answer is I have some ideas. All of this way predates my involvement in Planetary generally and in Venus community in particular, but a few things happened in the 1990s. So the Magellan mission to Venus, which was the NASA's last dedicated Venus mission until its announcement 2 years ago of these new missions. Magellan took near global radar image data. It was enormous, the data set. In fact, there's still a lot of low-hanging fruit left in the Magellan data, partly because around the time those data came back, and this ties to my bigger point, the Venus community began to kind of dissipate. There was funding for scientists for the following year or two after the Magellan mission, but that funding was cut short. Because NASA's always facing budgetary shortfalls, and it's always going to find a way of cutting things. And it's not the first time that Venus has nor was it the last that Venus got cut. So the momentum I described about missions never really was allowed to kind of take hold, I guess. There wasn't, to my knowledge, another Venus mission in the works toward the end of Magellan that the community could look toward. And around that same time, 2 other things happened. The Mars exploration program, which was established early in the 1990s, suffered 2 setbacks with Mars Polar Lander and Mars Climate Orbiter, but they had a huge win in the late part of the 1990s with the Pathfinder mission and the Sojourner rover, which really began to change the landscape, figuratively and literally, for how we would explore Venus, or Mars rather, because that led to the rovers. But at the same time, around 1995, there was a press release and a big press splash about the fact that purportedly a meteorite known to be from Mars looked like it possessed evidence of fossilized bacteria. ALH84001. In fact, if you've ever seen the film Contact, in that film, they've taken scenes where you see Bill Clinton give a press release about the machine. They actually took stuff from the press conferences he was doing in real life about this discovery. Now, I don't think anybody, except perhaps the Discovery team, thinks this thing contains alien fossilized microbial life from Mars. We think it's an abiogenic thing, which separately is a whole other conversation about how we would tell biogenic from abiogenic signatures. But the thing is, it got people thinking and talking about Mars. And Mars needed it, because after the Viking missions in the late 70s, a view emerged that the Viking missions, in a manner of speaking, had failed because the 2 landers were ostensibly life detection missions, and they failed to detect life. That result, for what it's worth, is still contended by some. But interest in Mars waned, and then in the 80s, planetary exploration largely basically ground to a halt. It started back in the late 80s and 90s with the launch of Galileo and Magellan, but Mars didn't really get a look in until Pathfinder, and it just happened around the same time people have been thinking about Mars as an abode for life. And I think that's whether that was enough on its own, or whether that was the vehicle by which proponents of Mars exploration could seize and advocate for sustained Mars exploration. There was not an equivalent momentum, nor was there a sufficiently strong advocate in Congress or in the community to push for sustained Venus exploration. So Venus was sort of allowed to wither on the vine. And that's part of the reason I think it has taken so long to get Venus back into NASA's sights.
And now, and I guess when we're recording this, there's some kind of sort of distressing news, but there are plans. There are 2 NASA missions expected to fly to Venus. There's a European Space Agency mission. There's a private mission in the works. So like 4 confirmed missions right now. What do you think changed?
I think a couple of things changed. Well, first off, I think the majority of the credit has to be given to the Venus community, the people who have been pushing for decades and who never gave up, pushing, making the case for NASA that this is a place we should be investing our money to explore. Those people really, really worked hard, and it's paying dividends now. I'm a relatively recent newcomer to the community. I do what I can to help advocate for this, but this was in place far before I got involved, and those people really have been pushing hard. Partly, those people have played a role in getting there. NASA has within the planetary sphere in the US, NASA has these advisory, well, they're not actually advisory groups, they're analysis or assessment groups, AGs, and there's one for Venus called VEXAG, the Venus Exploration Analysis Group. VEXAG is essentially run by volunteers, and it's a community group of people in the community who volunteer their time, researchers, scientists, engineers, early career folks, senior folks, who basically work with the planetary community generally, the Venus community in particular, solicit input, and then make those representations up the chain to NASA, saying, this is what the community's priorities are. There are other vehicles for this kind of thing too, like decadal surveys, but VEXAG in particular, in the last 7 or 8 years, seems to have really done a great job in pulling the community together and galvanizing a renewed push for why we should care about Venus. Now, the exoplanet angle has definitely helped. That has definitely been an avenue whereby within the last 10 years and even more recently, that the Venus community can point to this notion of looking for exo-Earths or eta-Earths, sometimes they're called, making the case that right now we are not able to distinguish that between an exo-Earth and an exo-Venus, and therefore understanding the factors that might lead to the outcomes, the climate outcomes you get on Earth and Venus are important for understanding how to interpret telescopic data from other solar systems. That's something that VEXAG has really helped pull together as part of like a narrative, and they've become that voice for advocacy that I think was missing for a long time in the 90s and 2000s and even the early 2010s. And this at the same time, I think there's also been a view that in the last several competition rounds where NASA holds these competitions for planetary missions, that Venus missions were highly ranked. They were deemed selectable, but they were not selected. And I think when that happens long enough, other people who are not within necessarily the Venus community start going, it's kind of weird. You guys are scoring really highly, but never getting picked. Why is that? It's never enough for any community of supporting any target to say it's our time, even if that might be how it feels. Because the point is, NASA will only ever fly missions on the basis of science. But Venus has never lacked for want of scientific rationale to go explore it. And I do want to emphasize the exoplanet angle has helped the narrative of Venus as a place we should be putting money into exploring. But it is only part of the thing. There were measurements taken in the 70s and 80s that suggested, and those measurements stand, that we have not gotten new ones or better ones yet, although one of the new missions to Venus will improve our understanding of that question. There were measurements taken in the 70s and 80s that suggested that at some point in the past, Venus may have had a lot of liquid water and it lost it. And that speaks to this habitability question. So we've had that question since the 1970s. We've had questions of what the ground is made of since the limited data, again from the 70s and 80s, returned by the Soviet Veneer probes. So we've had compelling questions that predate even the Magellan mission, which has raised a whole pile more. The exoplanet thing has definitely helped, and its timeliness is that it is, I think it's a confluence of a few things. Sustained work of decades on behalf of the Venus community, an awareness by other people in the community that Venus never really seemed to be getting the attention that perhaps it deserves, and the exoplanet angle. Those three things together, I think, have come together in this sort of timely fashion to have done enough to sway the pendulum at NASA to begin to seriously think about putting money back into Venus exploration.
Now, I mentioned, leading into my question, that one of these missions is a little under risk right now, and that's the VERITAS mission. So can you talk about what the problem is and maybe how we can affect a solution?
Let's do another cut here where I scream out.
Okay, sure, okay. Yeah.
So,
and we're back.
We're back. Okay. So the short answer is we don't. Okay. NASA's explained to us what's gone on. We don't really, I think, in the community, I don't think we have a very good understanding of exactly how we got to this point. But what transpired was, so first off, we can put the selections in context. So the most recent Discovery class mission competition, so this is a competition that ostensibly NASA would run every 2 years. It's now close to every 4 years. This is a mission that a PI, principal investigator, leads. And she or he assembles a team, they write a proposal. These proposals are cost capped in terms of the money the PI gets at around $500 million. In absolute terms, a huge amount of money. In relative terms of Planetary, not that much money. So these are considered medium class missions. And in the last 2 rounds of Discovery class competitions, NASA selected 2 missions. In 2017, they selected the Psyche mission, a mission to a metal asteroid, and they selected the Lucy mission, which launched about a year ago. And Lucy is going to go visit the Trojan asteroids around in orbit, or in the same orbit as Jupiter. In the most recent selections in 2021, NASA again picked 2 missions out of a short list of 4, and they picked VERITAS, its first global radar mission since Magellan, and promising to return data at much higher resolution with modern technology and measuring a whole pile of stuff we've never had before. And a mission called Da Vinci. And Da Vinci is going to be similar to Pioneer Venus, a mission that NASA flew in the late 70s, where there'll be a carrier spacecraft that will deploy a probe about 1 meter across, a big titanium ball. This thing will fall through the atmosphere, taking atmospheric measurements and getting into the atmosphere for the first time since Pioneer Venus, as far as NASA is concerned, in 1978. So it selected these 2 missions in June of 2021. There was much rejoicing, and then even more rejoicing because the following week, the European Space Agency announced that the winner of its most recent competition for medium class mission was, there were 2 shortlists. One was an astrophysics mission and one was a Venus mission, and it picked the Venus mission, a mission called Envision, the main instrument for which is being supplied by NASA. So NASA is essentially paying for 2.5 Venus missions. So verily, great. We're back on Venus. And of course, we're starting to see this now, people turning up to conferences and workshops. The more you start putting money into missions beget missions. They beget a community interest in these questions. You get new people who've not thought about Venus prior to now getting involved. And come one, come all, I say. Get in, help us study this thing. Okay, now I mentioned that in the last 2 rounds of competitions, NASA picked 2 missions. The 2 missions from the previous round, Lucy and Psyche. Lucy launched, it's in space, suffered a minor issue with one of its solar panels, but it's otherwise healthy. It's on the way out to the Jovian space. Psyche encountered a problem last year where it transpired it was going to miss its launch window. Now, because missions like this tend to go to very specific places, they have launch windows. If you miss a launch window, even if you may have a backup, say, a year later, that's problematic because it means that you're paying to keep that thing on the ground, and that costs money. Now, Psyche's delay was largely attributed to shortfalls in management at the Jet Propulsion Laboratory, based in Pasadena, California, one of the NASA centers, and this one administered by Caltech for NASA, where through a variety of reasons that I'm not terribly privy to, but were highlighted in an independent review board that was a report of which was published late last year, Psyche misses launch window. And one of the consequences of this was that NASA had to take a charge on paying for the overrun to get Psyche off the launch pad this fall. One of the other fallouts of this whole thing was that there were the systematic management issues at JPL that this review board identified necessitated that NASA take some kind of action against JPL. And so what we learned as a community in November of last year, so still not that long ago, about 5 months ago, was that NASA was going to slip or delay the VERITAS mission by no fewer than 3 years. This was a real punch in the gut for a couple of reasons. One, the VERITAS team were on schedule and on budget. And NASA has repeatedly explicitly stated this is in no way the fault of the VERITAS team. The VERITAS team, the science team, has been given a trickle of money, as these things go, to keep going for the next few years. But the engineering folks who were working on the concept have been pulled off and scattered to the four winds to address shortfalls, not really on the Psyche mission, other big capital projects that JPL is responsible for, including two planetary flagships, Europa Clipper and Mars Sample Return. So it was a good punch for a couple of reasons. One was to the VERITAS team for them having done nothing wrong. And the other thing was that the money for VERITAS, the Psyche delay seems to have cost NASA about $80 million. Now, that's a lot of money, but it's of order the kind of money that, say, VERITAS would have consumed in a year. So one might expect perhaps that VERITAS was delayed by a year, let's say, to sort of put that money into Psyche, get Psyche off the pad. So the decision by NASA to delay VERITAS by no fewer than 3 years came as a huge surprise. Now, NASA has not been forthcoming with the details of where the rest of the money that was supposedly in the budget when they picked both VERITAS and Da Vinci in 2021. NASA has not explained where that other money has gone. It's likely gone to other projects that were facing cost overruns. I don't know what they are. But the point is that money is gone.
Yeah, and when your engineers go and work on other projects, that's a really hard bell to unring.
Because what's going to happen is, if it were a case where there was a cessation or a pause for, say, a year, there's some kind of institutional memory left over, and it's not as hard to pull the team back together. But precisely to your point, when those people are brought back for the engineering side of things, and VERITAS was not far enough along in the formulation slash implementation of it to, I think it wasn't far enough along to be invulnerable to this kind of thing. So if you're looking at it from the perspective of NASA, and you have these other shortfalls and these overruns, and then you have these issues with JPL, and you know what? VERITAS was a mission being run by JPL. The other Venus mission, Da Vinci's, been run out of the Goddard Space Flight Center. So it wouldn't, on paper, have made much sense to pull people off that project. But it was really, really hard to take in terms of the Venus community. But we've learned since that it doesn't seem that it's going to be a 1 year delay. It doesn't seem that the Psyche issue is proportionate to the delay that the VERITAS mission is facing. And that speaks to the fact that NASA has overcommitted itself in other regards. And VERITAS, a relatively small mission in the realm of planetary exploration, was an obvious thing for them to functionally cut. Now, they've emphasized it's not a soft cancellation. They've made the case. We've heard the new Associate Administrator for Science, Nicola Fox, who just took the job a couple of months ago. She's been very clear that VERITAS will fly, but to your point, it's going to fly potentially now no earlier than 2031, when they were targeting a 28 launch. So not only do we have to wait longer for data, that also has downstream impacts on the Da Vinci and the Envision missions as well, which none of us really anticipated coming.
I mean, as two non-Americans, how do we help NASA, and how do we help influence NASA to get this mission back on track? I mean, is there anything people can do?
So that's a great question, and I think there is something we can do. But you know what? It's not about influencing NASA. So NASA works within these tight budgetary constraints. NASA seems to have rolled the dice in terms of what its budget's going to look like for the next few years. And right now, they are planning to add money back in for VERITAS, but they are subject to appropriations by the U.S. Congress. So the biggest group that we in the community, and certainly internationally, but certainly those of us who were living in the US, those of us who were able to vote, for example, in the US, which does not include me, but certainly people who are able to vote who live in the US, the Planetary Society, arguably the most effective and powerful advocacy group for planetary research in the world, and particularly within the US, they have the ear of people on the Hill, Capitol Hill in Washington, D.C. The Planetary Society has done a really good job quickly stepping up to push for a reinstatement by Congress of funds for VERITAS to get it on the pad sooner than this 3 year delay would otherwise see. So folks can go to planetary.org, and there is a Save VERITAS link on that page, and there is an option to mail or email your local congressional representatives, both in the Senate and the House, and ask for them to put this money into NASA's next budget. Advocating to NASA probably isn't going to be all that much use, because NASA has said they want to fly VERITAS. They will when they can, but they're budgetarily constrained right now. The folks who control the purse strings are Congress. Get in touch with your representatives if you can, if you have some, if you live in the US and you're able to vote. And planetary.org is making it easy for people to do that. That is the best, most effective, I think, thing people can do right now to try and help save VERITAS.
Right.
Now, I'm doing air quotes, like I said, it will fly. But this is a real setback to this supposed era of new exploration of Venus, particularly when it was through no fault of the VERITAS team themselves.
Well, we'll go back to infecting other people with our obsession for Venus, and that will be doing our part. I want to go back to those big mysteries, and one of the big mysteries is the level of volcanism. And you worked on a map of Venus.
Right.
And you found all its volcanoes and put them in one handy location.
Yeah. So I gotta say, props to a graduate student who's working on her PhD with me, Rebecca Hahn. Becca is the person who spent a not insignificant portion of her life. I guided and I offered help, and I helped her pull the paper together through publication, which we published about 2 weeks ago with Journal of Geophysical Research Planets. At least through the end of the next week, it is free to access online for folks. You don't need a subscription, so you'll be able to get the PDF. And basically, this work emerged out of questions Becca and I talked about for a while about how many volcanoes are on Earth, how many volcanoes are on Venus. What would that tell us? Because, and this is something that will underpin some of the later work in her doctoral project, we don't know how many volcanoes are on Earth, because the majority of them probably are under the ocean. And we do not have global high resolution, we call it bathymetric, topographic data that we can see these things. Ships tend not to just map the seafloor for no reason. They tend to do them in particular areas. And so we actually don't know how many volcanoes are on Earth, which means by extension, we don't know how active volcanically Earth is. We know the majority of stuff comes out of Earth at the seafloor centers where new tectonic plates are made. We know that. We've known that for about 60 years. But in terms of the number of actual distinct eruptions, we don't know the number. And so this was something that started the conversation for doing Venus, because Venus has no oceans. It may have once had oceans, but it doesn't have oceans anymore, which means we can see almost the entire surface. Now, it just happens to be that it's no small feat to map all the volcanoes on Venus, because Venus is 3 times the land surface area of Earth, right? So think the land we have and multiply that by 3. That's what we have for Venus. There's a lot of land. So Becca, over the course of a couple of years, basically mapped, we've known for a while, and she was able to kind of verify this, where the big ones are. But no one's ever taken the time to go through and look for all the small ones. Now, one thing we want to be clear is the overwhelming majority of volcanoes in her catalog are small ones, somewhere between 1 and 5 kilometers in diameter. Out around that scale, we think we're pretty confident we've got everything down to about 5 kilometers in diameter, which is pretty small with the data we have. 5-kilometer volcano is not small. As a thing goes, but in terms of the data, it's pretty small.
Can you give us an analog? Like, what's a 1 to 5 kilometer?
That's a great. Let me actually, off the top of my head,
Mount Helens?
One, because those ones are much bigger, and the big ones are the famous ones are big. But if folks have ever gone to, for example, to the volcanic fields that are, say, SP Crater, or there are places in New Mexico, Arizona, where folks craters of the moon. There are lots of small volcanic edifices, and those things are only a few hundred meters across, and yet they're pretty big when you're hiking them. So a 5-kilometer diameter volcano is not a small thing.
Yeah.
It's not a huge thing, and certainly the really big ones we have on Earth, there's 2 types of really big one. There's things like Mount St. Helens, which are a type of volcano called a stratovolcano. We don't think actually forms on Venus for a variety of reasons. And then the really big ones are things like Mount Etna, or some of the Canary Islands, or the Hawaiian Islands. Those things are what we call shield volcanoes. There's plenty of those on land as well as in the oceans. And Venus has loads of those. In fact, Venus has volcanoes that are bigger than some of the volcanoes on Mars. They're not taller, but they're broader. Because the really tall ones are on Mars. But the thing is, what basically the goal of this was to try and get a sense of where are there volcanoes and how many are there. Now, Becca's catalog contains about 85,000 volcanic edifices.
And so, sorry, did she identify these? Like, these are previously unknown volcanoes that she found?
The majority of them are. And she went and it's not that we use new data. It's that part of the reason is, not to put too fine a point in it, a grad student is the kind of person who could do this because of the sheer amount of time it takes to do. And most people, like I said earlier in our conversation, a lot of people who were doing Venus, including grad students, kind of stopped doing Venus in the middle 90s. And there have been volcano catalogs published by people since then, but they would not have had the time to put this much time into zooming in. There's also a big component of modern computing capability, which is really interesting to me. So we talked briefly about the fact that about a month ago, a paper came out finding evidence for this new volcanic activity on Venus that was previously unrecognized.
Yeah, we'll talk about that in a second.
Right. But part of the reason that enabled that to be done was one, the Robbie Herrick, the lead author of the paper, said in lockdown, he found himself on a lot of Zoom calls and had time in his hands. So he had time to go whilst on these Zoom calls, trawling through these voluminous data for Venus. But also, when these data were first acquired in the early 1990s, they were humongous. They were gigabytes. And no one had either the ready means of sending those data to people in the mail, or simply having the computing ability to go and look at them. So often these things were printed out in hard copy at NASA centers like JPL, where people were, if they were there, were able to go and explore. But no one had ArcGIS or ArcPro on their computer running a powerful NVIDIA graphics card. And so a lot of stuff couldn't be done at the time. Whereas modern desktop computing allows someone like Becca to go and have the time and the resources to actually go and zoom in and pan and zoom out and put the time into identifying, at least as point locations, this myriad of 85,000 edifices. Now, an important point is there are lots of parts of the surface of Venus with Magellan data, which is what she used, where the resolution is too low or the signal to noise ratio is too low, i.e. the data are literally noisy and it's kind of hard to see stuff. And there are many, many places where we are sure there's more stuff, but we cannot see it well enough to map it, which means that there's almost certainly a boatload more volcanoes on Venus that we've yet to identify.
What's the resolution?
Can't see them. It's about 100 meters per pixel, which means to see a feature, it really has to be 5 or 6 pixels across. And even then, because of the nature of radar, it's not acquired the same way as like a regular photo. There's a lot of speckly noise, which is sort of governed by the physics of how radar data are acquired. Really high signal to noise ratio data will have little speckle, and it'll be easier to see subtle things. That's what we have with modern radar data sets for Earth, for example. There's the European Union's Sentinel missions can do it, for example. And these new missions, the VERITAS mission we talked about, which is delayed, and the European Space Agency's Envision mission with a US radar, they will both be able to take much higher resolution at much better quality. So they're going to be unreal. They're going to show us features and things we haven't even thought of looking for yet, including we anticipate finding these smaller edifices that we didn't see in our catalog. So we can already make some predictions as to where you should point these radar instruments at, what to look for. And then, of course, that all gets to what's the rate of volcanic activity? Where is volcanism concentrated? Where was it active once and isn't anymore? What does that mean for the stress state of the lithosphere, the thick outer brittle layer this stuff has to come through? All these kinds of science questions are enabled by having these kinds of catalogs.
Yeah, when you think about Mars Reconnaissance Orbiter, Lunar Reconnaissance Orbiter, resolution sub 1 meter per pixel, I hear 100 meters at Venus. I've even reported that, and I'm like, that's got to be a mistake. Like, I'm getting this number wrong, right? No, 100 meters.
But I will. So, yeah, to the credit of the Magellan engineers, 100 meters per pixel of a planet as big as Venus is a gargantuan data set, and they may not. I think they really pushed the Magellan radar to its full capabilities. But back then, there probably wouldn't have been much more of a use of taking higher resolution data because they wouldn't be able to process it. However, with modern radar technology, certainly for the VERITAS mission, we're anticipating 30 meters by 30 meters globally, but much higher signal to noise ratio. So it'll be crisper. There'll be much less speckle. We'll also have much better topographic control. And that speaks to a whole pile of other things it'll it'll improve how the radar data look, and it will also give us a huge new data set and much higher resolution than the existing data sets to answer a lot of the questions we have in geology require 3D data. We'll get those from Envision and VERITAS. In places, Envision will be able to take 10 meter by 10 meter pixels. Now we're getting close to some of the contemporary relatively high resolution data from Mars. Originally, in early plans for Envision, it might have gone as high as 3 meters by 3 meters for very, very small select areas. That capability may still be possible. It's not clear. even getting a handful of places at 3 meters by 3 meters would be revolutionary, because it's not going. We have a few. We've a relatively speaking handful of 3 meter by 3 meter pixel data from Mercury, because at the end of the mission that NASA flew to Mercury Messenger, it got low enough for reasons I'm going to skip, that it was able to take very high resolution photos, because its global image data for Mercury is 167 meters per pixel. It's even cruder than radar data for Venus. But there are places where we have 3 meter by 3 meter per pixel data for Mercury. But just like for the moon, because Mercury has no atmosphere, its craters all the way down. And you can be a bit hard pressed to tell whether you're seeing 100 meters per pixel image or a 3 meter pixel image, because it kind of looks the same. Whereas for Venus, because of its thick atmosphere, there are no craters smaller than 3 kilometers in diameter. We are going to see some funky stuff on the surface of Venus at 3 meters per pixel, even 10 meters per pixel. And it will literally open up a whole new world for us.
All right, so let's talk about this evidence of active volcanism on Venus.
Right. So a paper came out about a month ago by Robbie Herrick and Scott Hensley, and they used Magellan data. Again, I cannot emphasize enough how much stuff there is to still do with those data. And what they did, what Robbie had started to do, was basically focus on, let me give you some context to it. The Magellan mission, flown in the early 1990s, had geologists and geophysicists on the team, and they knew there was a possibility they would look for features that had changed over the 8 months or so between each successive phase of imaging stuff. And so the idea of looking for something on Venus that indicated change over the Magellan mission was not new. The problem is twofold. One, the radar data, like I've said, are not particularly high resolution. They're not all that good in terms of noise. And depending on, I'm going to skip over the details because it gets kind of arcane, but there are different ways the data are taken. And depending on which way they were taken, the look direction can differ, and features that might seem very prominent with one image could be absent completely in the other. And that's not because they went away, it's because the radar didn't see it. Because there are kind of specialties and nuances you have to keep in mind when looking at radar data. So people spent a lot of time during the mission looking for evidence, a new lava flow or a flow that was longer or a new volcano or some other evidence that something had changed between successive phases of imaging over about 8-month intervals. And nothing was ever seen that was unequivocal. I've done this. There are plenty of places where things seem to change between successive images, but you can't say with confidence that it's a real thing and not a radar thing. So Scott and Robbie principally, like he said, on Zooms in the early part of the pandemic during the lockdowns, would basically go, and he focused first his survey on places where we've reason to think there's relatively active volcanism because of other geophysical and geological observations dating back to Magellan. And in that survey, he looked for evidence of stuff that had changed. And he found a few and was able to whittle it down to one particular thing. And then he partnered with Scott Hensley, who is an expert in radar analysis and processing. And between the two of them, they were able to simulate what they think they were seeing on the surface with essentially like artificial radar to verify that it was a real thing and not some radar artifact. And what they were able to show was that, yes, this is a real thing. Now, the thing that's changed in 2 successive images is a few pixels, and it's a few millimeters on a printed page. But what it actually is a hole that was around 2 kilometers across became 4 kilometers across over the course of 8 months. It was a gargantuan surface change. It just looks relatively small because of the quality of the data.
And what's the underlying volcanic process that would cause this?
So the shorter answer is we don't know. The longer answer is, I think my view is that the best, and I wasn't involved in the paper, but my best analogy I can think of is in 2018, the summit caldera on Kilauea got substantially bigger because there was a big eruption downhill, and that's what hit the Lanolea Estates, and it caused a lot of people their homes. And that's basically the big flank eruption that happened in the summer of 2018 in Kilauea. And if you've seen before and after pictures of the summit caldera at Kilauea, which is a famous place people go to look at, often there's a lava lake sitting there, it got a lot bigger. There's portions of the road which are down now dropped into the caldera, and it's just a lot bigger, a lot deeper, a lot wider. Probably something like that. Now, when that kind of thing happens, usually you expect to see lava come out of the ground somewhere. It may not come out of the caldera, but it'll come out in the area somewhere. There is a place in the paper they identify that potentially could be a new flow, but the radar data are equivocal. But what is not equivocal is that the hole got a lot bigger, and it's not an artifact of radar. It's not some glitch in the sensor. It looks to be a real change. And for something to go from 2 kilometers in size to 4 kilometers in size, we don't. It probably didn't take long to happen, but it happened at some point in the intervening 8 months between those images being taken. That's a humongous geological event. Now, maybe not in the planet's history, but over the course of a few months, it's a big deal. It would have had a big seismic signature as well. There'd be a lot of tectonic activity. They found that in an area where one would reasonably expect to find it. And as Robbie is at pains to point out, he spent the time he covered about 1.5% of the surface. So the fact that this is the only definitive, I think, so far evidence for something changing is less to do with the rate of activity on Venus and more to do with the limitations of Magellan data. And this is exactly the kind of thing these new missions like VERITAS and Envision are designed to and will test.
Were there a lot of regions that were checked multiple times by Magellan?
I don't know. Well, yes, certainly there were a few places. Really, it comes down to, so Magellan operated in a series of cycles, and the first 3 cycles were basically image cycles. But the quality and ability of the radar instrument was degrading through each of those successive cycles. So by the time they did cycle 3, they covered much, much less of the planet than cycle 1. Now, the reason 3 matters is cycles 1 and 3 have the same look direction. The angle of look is a little bit different, but it means that you have fewer of these radar artifacts. Cycle 2 is a different look direction and raises the possibility that you're seeing stuff that isn't real, and then you have to be careful, which is what the Herrick and Hensley paper, they dealt with that quite well. So again, it's a function of limited data and relatively low resolution data with high signal or low signal to noise. It's sort of a confluence of things. Again, that is not to rag on Magellan. It really did some amazing stuff, but it just speaks to the fact that we are looking at a data set designed with a radar instrument built and designed in the 1980s. So we really do have the ability to do much, much higher resolution, much more capable stuff now, and also beam back more data from Venus than we were able to in the early 1990s, and manage these data on desktop computers and offices now.
And if not today, then tomorrow. I mean, I think that philosophy of taking data that you can't handle makes a ton of sense. And we're seeing a version of this with, say, the Vera Rubin Observatory, which is going to be sending torrents of data out on the internet where the files are way too big for anyone to try and work with, that they're going to do a lot of data post-processing just to get into the hands of astronomers. But 10 years from now, someone will on their desktop download they'll download the whole file and they'll just go like, find me all the black holes. And
pretty much, right? ChatGPT will have emerged into some sort of horrible overlord, and it'll be able to. Like the point is that you're trying to future-proof these things. In a way, there's a parallel with the Apollo samples. NASA has, over the last few years, allowed research teams to open some of the previously sealed samples that were sealed on purpose back when they were collected in the late 60s and early 70s, knowing that laboratory techniques would improve in decades to come. And we'll see the same thing with the Artemis samples or Mars sample return samples when they all arrive back on Earth. That the idea is that we know that at some point in the future we'll have better capability. So let's keep some of the samples to the side and let's leave them until we're ready, even if that's not till 2100. It's the sort of thing, and this speaks to planetary exploration generally. It's a little like cathedral building. Cathedrals, at least the big ones in Europe, they all lasted far longer than a single human lifespan. And so people began building them knowing they wouldn't see them at the end, but knowing that they were contributing to something bigger than themselves. Planetary is a great archetype of that kind of activity.
Yeah, it's a really fascinating philosophy to go with that, which is that we don't know how to work with it today, but we know that we can at least get the data home and someone will be able to work with it in the future. Now, I want to talk about some of those scientific mysteries that you brought up early on. And I know for my audience, a bunch of them are pretty compelling and I get a lot of questions. So hopefully I can just pass these questions along to you. The one is just this idea that Venus doesn't have a planet-wide magnetosphere. And yet it is roughly the same size and mass as the Earth. Mm-hmm. Gravity, it's got gravity, it's made of rock, it has metal. Why doesn't it have the same kind of internal dynamo that Earth does?
So the short answer is I don't know.
Okay, so another
the
screaming...
longer answer is... Well, this one, because this one actually is something it feels like it's in my control to potentially actually help contribute to. The longer answer is that no one knows, but there are some ideas why. So first off, it's true that it does have a magnetosphere, but it is an induced magnetosphere. The solar wind induces one. And the reason that's important is because it's sort of the flip side of not having a magnetic field or having one, which is to do with atmospheric loss. So I'm going to talk about that real quick. There is a prevailing narrative that the reason Mars has so little atmosphere is because it has no magnetic field that it generates itself, and therefore it loses its atmosphere to the solar wind. And that's true. However, Venus has no magnetic field it seems to generate itself, and it's losing atmosphere to the sun, and yet it has 90 times more atmosphere than Earth does. So clearly, magnetic field is not all that. And in fact, depending on, and this is where we're getting to things like escape mechanisms, and I'm not going to talk about that kind of stuff because that really is beyond my wheelhouse. However, it turns out that in some cases, a magnetic field actually speeds up the loss of certain types of particle in an atmosphere. The biggest reason why Mars doesn't have a thick atmosphere is because it's small. At least this is my working hypothesis. It's got a small mantle. It degassed, which is to say that the volatiles in that mantle, things like water and CO2 and H2O and H and C and everything else, most of that stuff came out early on. And yes, it was lost to the wind, to the solar wind. But the mantle wasn't big enough to be able to replenish it over 4.5 billion year timescales. Whereas in the case of Venus, it almost certainly is. And so too with Earth. We now know that to within about the same rate, Venus, Earth, and Mars all lose atmosphere at about the same rate every year. And the reason we still have an atmosphere and the Venus is a giant atmosphere is because probably both worlds are volcanically active. And the reason they're volcanically active is because they've got a big heat engine, because they've got a big ass mantle full of volatiles. At least that's one possibility. So it turns out magnetic field may not be all that important to life. In terms of why Venus doesn't seem to have a magnetic field, there's two things we think a planet needs to have: its own dynamo, its own really nicely powered dipole magnetic field. So think bar magnet. It needs to have a spinning iron liquid core, at least if you're a rocky planet. But you need some energy driving that spin. It's not the planet's rotation itself, although it's not uniquely the planet's rotation itself. And what we think is helping Earth's magnetic field be generated is that the inner core is forming. The inner core is freezing out. Now, it's kind of weird to think about freezing in the context of 5,000 Celsius. But the liquid iron is turning into solid iron, which is changing phase, which is a form which is you can call freezing. And in doing so, releasing energy. And this energy is helping drive this flow of iron in a fairly uniform, coordinated way, such that it's able to generate this dipole magnetic field. So it could be that if there's no inner iron core inside Venus at all, you could have a swirling outer liquid core. It wouldn't be outer liquid, it'd be the liquid core. It could be swirled all at once and it wouldn't generate a dynamo. It could be that the inner core is all that's there and there's a solid ball of iron, in which case there's no liquid at all. So, or the liquid could be swirling around a ball of a solid iron, but if it's not swirling in a fairly uniform way and it's sloshing around instead, it won't generate a powerful dynamo, but it could be generating some sort of weird, messed up magnetic field. Now, here's the thing. We don't know for sure that Venus doesn't have its own magnetic field. We're pretty sure, but it is possible that it does have one today, but it's extremely weak. And we've never had a spacecraft go low enough to be able to definitively rule that possibility out. It's probably not a big possibility, but it is possible. And so that may speak to the fact that the interior properties of Venus, chemically and physically, are not quite the same as Earth. Understanding why Venus doesn't have a magnetic field, whilst understanding what its interior looks like, for example, would be hugely important to help us understand things like how magnetic fields come to be generally. How does Mercury have a magnetic field today, albeit one that's 1% the strength of Earth, when Venus doesn't? And here's the other thing too. As far back as we have reliable samples, Earth has had a magnetic field. We do not have 4 billion-year-old samples of Earth that show a magnetism. So we don't know when Earth's magnetic field arose. We do know that the moon had a magnetic field very, very early on. It didn't last that long. We know that Mars had a magnetic field that shut down somewhere around 3.8 billion years ago. And we know that Mercury had a magnetic field at around 3.8, 3.9 billion years ago. What we don't know in the case of Mercury is whether it's the same field that's today, because it turns out it's extremely hard to come up with models that would allow that. Or if it's a separate magnetic field. It had one early on, like seemingly Mars and the moon did, and then that shut down for some reason, and then somehow started up again.
So
we don't know the answer to any of these questions.
So our magnetic field could be just a phase.
Yeah.
And not as necessary for the rise of life on our planet as we have all been led to believe.
It might not be. Certainly, we know the magnetic field changes, it waxes and wanes, it moves. We know that occasionally the polarity of the dipole at least flips. And when that happens, and the most recent one was something about 780,000 years ago, there is no big giant mass extinction tied to that. Mm-hmm. So that's not to say that a magnetic field isn't important. I'm sure it is. But it might not be the only may not be a prerequisite of a world developing life, particularly that life we're developing in the oceans,
Right.
which is where we think it did
Right.
now.
You're under a meter of seawater and you're fine from cosmic rays and
You're
solar radiation
totally,
and anything.
exactly. Yep.
And
we've only had land animals for the last 540 odd million years.
That's interesting.
And we don't know when the inner core on Earth began to form, but we think it might be as recent as around 1.3 billion years. So it could be that for most of Earth's history, it didn't have a magnetic field.
So what about plate tectonics?
Oh my God, that's literally a whole other interview. Like, let me I'm going to answer this by just this brief anecdote. In 2020, the kind of peak of lockdown, when Robbie Herrick was tootling around Venus with ARC, and I was too, there was a set of meetings, basically Zoom colloquia organized online for folks. I think it was organized in an Australian university, but it was open to anybody. And the first one that I joined, about geodynamics and about early Earth and about really interesting stuff. Not a huge amount of planetary, but thinking about what plate tectonics was on Earth. And the one I listened into first was a grand 2-hour debate. When did plate tectonics start on Earth? And it was a fascinating thing to listen into. But at the end of the 2 hours, they hadn't gotten to the topic because they had spent that long debating what the word plate tectonics meant, because it means different things to different people. So the question of what plate tectonics is today on Earth is not settled. We don't know how long it's been in this current state. We don't know what initiated. We don't know what the early version of Earth looked like, whether it had plate tectonics that resembled the thing we have today or some other version of it perhaps. And so trying to extrapolate that to Venus is even harder because, like I say, there isn't a uniform set of views as to what constitutes plate tectonics for Earth. There is, and this is some of my researchers speaking directly to this question, there is, I think, good evidence in the rocks, particularly the oldest rocks we think are preserved on Venus, that Venus may at some point in its past have had a lot of stuff moving around laterally, moving around horizontally on the surface. That is one of the hallmarks of plate tectonics. It's not the only one. Whether that means that Venus had plate tectonics in its past is a humongous open question, and one that we are going to be able to take a step forward in answering with these new missions. It may not perhaps definitively answer the question, but it's the sort of thing we have to try and answer to figure out why Venus seems so different to Earth today.
And that does seem to, at its heart, help with the livability on Venus. Like without the plate tectonics, you don't have that rock cycle. You don't have that sequestration of carbon dioxide.
So that's the thinking, right? The thinking is that certainly as far back, like I said, as far back as Earth, as samples we have, and we have mineral grains that seem to go almost back to very soon after the formation of the moon. It seems that Earth had conditions amenable to liquid water being stable on the surface. And for liquid water to be stable, you have to be above 0 Celsius and below 100 Celsius, plus or minus. And so the idea is that Earth seems to have been clement, if you like, for most of its history. What I think we're learning from worlds like Mars, where you seem to have this relatively short period of time where perhaps it wasn't ever habitable in the sense that Earth was, but there was liquid water ponded on the surface for a while, at least in places, and perhaps episodically. Certainly, it seems keeping a planet habitable, meaning where it's in that temperature range that liquid water is stable, that seems really hard. And certainly the idea of plate tectonics is, like you say, a means of sequestering carbon, keeping carbon out of the atmosphere so you don't enter a runaway greenhouse effect. Having the ability to do that seems to have been key, we think, to retaining Earth's habitability over the past at least 3.4 billion years, which is as long as we know life has been here, but likely much longer. And I don't think many people would have an issue with the idea that life was probably on Earth for more time than that, but the issue is that finding it preserved in the rock record is very difficult. If Venus was ever not the hellish world it is today, then the thinking goes that it must have been able to somehow have kept its climate relatively clement. And the way we know Earth does that is through plate tectonics. So it speaks to the idea that it may be, people have proposed, hypothesized that plate tectonics is in fact a core requirement for life. I don't know if that's true, but it certainly seems to be pretty likely a requirement for a large world to remain habitable in terms of liquid water being present on its surface for extended periods of time. Maybe plate tectonics is not required for vent life, hydrothermal vents in a large icy satellite moon or water world, or a world where it's not orbiting a star, it's been ejected, it's only so-called rogue planets. Maybe plate tectonics isn't all that, but if you want to keep liquid water on the surface of a planet, certainly plate tectonics seems to be a very efficient, perhaps the system of keeping that planet comfortable over geological time.
So to bring it back to that idea of Venus as an exoplanet, how does sort of, I mean, I wish we could come have this conversation, and we will, I'm sure, 10 years from now, after we've got the data in from VERITAS and Da Vinci and Envision and all of this kind of stuff to give us the much more detailed information. But for now, as the exoplanet hunters are looking through the JWST atmospheric data, as the new missions are coming online, Ariel and some of the bigger ground-based telescopes, they're going to start getting some pretty good analysis of the atmospheres of these other planets that are potentially in the habitable zone. So what, if you looked at over their shoulder and go, oh, that's a Venus, you know, what would you be looking for?
So one of the big giveaways of Venus is the almost pure CO2 atmosphere. It's 96.5% CO2. It's almost actually the same composition as Mars, just much more air. So finding a world with a very definitive CO2 atmosphere signature and very, very little or no water would be a powerful indicator that you're seeing a world that seems to be in this so-called runaway greenhouse state, where it is dominantly an atmosphere that is very, very dense, that's sufficiently dense that it is that it has high surface temperatures. And I think that's one of the things we would use to characterize an exovenus. Of course, if you found a small world with CO2 in its atmosphere, that might be Mars. So that doesn't mean it's on a runaway greenhouse effect. It does mean it probably doesn't have liquid water, but it doesn't mean that it's a bakingly hot, scalding surface, because the surface of Mars is generally pretty cold. But if you found an Earth-sized world with CO2 and almost nothing else in its atmosphere, that'd be a pretty good indicator that it's a Venus-like world. And that's where it gets interesting, because then you want to know, where is it with regards to its sun? There are, and I'm going to keep this brief, there are two prevailing models for how Venus came to be. One is that it was always the way it is now, because purely as a function of how close it formed to the sun, it was never able to cool down enough and retained all that energy from the formation and impacting and everything, and just stayed hot. And it's been that way forever. It's in some sort of equilibrium. The other possibility, hinted at by these data I mentioned earlier from the 70s and 80s about the potential that Venus has lost water in its history, is that at some point early on, Venus may have been able to cool down enough to condense what was probably a steam-rich atmosphere, which probably the hellish version had too, with that steam eventually being lost to space. But if Venus was able to cool itself down and condense that steam, you'd get ponds and seas and oceans. And then if you're going to retain them, you're going to need something like, say, plate tectonics. That idea largely hinges on the fact that if it's scenario one, if Venus was always planet hell, it was because of how close it was to the sun, which means if you found a large rocky world about the size of Earth or Venus and you found that it was CO2 dominated atmosphere, and you could infer, there are even other things you could look for, like radio waves, that might potentially tell you the surface is actually hot. But certainly if you could detect that CO2 atmosphere signature in its atmosphere, and it was close to its star, it was inside the so-called habitable zone for that star, which you could calculate, that would lend pretty strong support to the idea that if you have a world, no matter how beautiful it might start out, it's going to end up like Venus if it's close to its star. That'd be pretty strong evidence. If, however, Venus was able to cool itself down and its distance to the sun didn't matter that much, then you can imagine a scenario where you could detect a large exoplanet, size of Earth or Venus, and it's either relatively close to its star and doesn't seem to have a CO2 rich atmosphere, or it's quite far from its star. Maybe it's well within the habitable zone, but it has a CO2 dominated atmosphere. Well, then that might suggest that planetary distance doesn't matter that much, and something else triggers a runaway greenhouse effect. Now, in the case of Venus, if you took that second scenario where it started off pretty clement, it was able to condense the steam in its atmosphere, no matter the fact that it was close to the sun, and then at some point from that time to today, something went wrong. The only mechanism that we can easily think of, as geologists at least, is some sort of massive set of volcanic eruptions taking place at around the same time, dumping a humongous amount of CO2 to the atmosphere fast enough to overwhelm whatever mechanism the planet has been using up to that point to sequester its carbon dioxide, such as perhaps plate tectonics. We know that some of the biggest, including the biggest mass extinction in Earth history, was tied to a gigantic outpouring of lava in what is now Siberia. We don't understand what governs those kinds of events, those so-called large igneous provinces. We don't know how often they happen. They don't seem to be necessarily periodic, and they don't seem to be predictable in terms of space. And so if for some reason the world had 2 or 3 of those go off stochastically, At the same time, might that be enough to trigger a runaway greenhouse effect? Well, if you found an Earth-sized or Venus-sized world orbiting a star far from the star, but it has a thick CO2-rich atmosphere, that would certainly be consistent with the idea that that planet's undergone a runaway greenhouse effect for reasons that are not tied to its distance to its star. So that's the kind of thing we need to start measuring.
Yeah. And so, let's imagine that we build the Venus Sample Return mission, which is like some kind of blimp that hovers in the atmosphere in Venus, the cloud tops. It sends some kind of drilling platform down and is grabbing core samples and bringing them back up to the balloon. And then after it's got a few hundred, it sends them home.
And let me just say, I cannot wait for that.
I know.
mean, that's going to
good news. Yeah, no, it's in the works right now. Could you get answers to those questions, do you think?
You could definitely help answer that question. There's a couple of ways that would tell us. So the Da Vinci probe, this is the second of the two missions that NASA picked 2 years ago. Da Vinci is going to go and hurtle through the atmosphere. It's going to free fall for about an hour, and it's going to take a bunch of measurements at different parts of the atmosphere, below which where we think the point is that the atmosphere is relatively well mixed, and the thinking goes that if you take a sample there, you could take it anywhere. Now, Da Vinci is going to be a game changer in terms of the stuff it's going to tell us for a couple of reasons. That doesn't mean that it's necessarily going to give us all the answers. Having a balloon that would float through the atmosphere for, say, weeks or months at a time might give us much greater precision and be able to tell us how some critical components of the atmosphere's chemistry change with day, night, latitude, longitude. But Da Vinci is definitely going to go a long way toward helping us understand the history of the planet by looking at particular isotopes and abundances and ratios of isotopes of noble gases in the atmosphere. So Da Vinci is going to help with that. Understanding what the rock is made of would definitively be a humongous step forward. And not just, so about 80% of the surface of Venus is covered in volcanic plains of various ages, but certainly those plains, it turns out if you take a sample of basalt on Earth, that will tell you quite a bit about the interior. It doesn't tell you everything. There is no one sample you can take anywhere of Earth or probably any world that will tell you the whole world's story. But you would definitely want to get some samples in the plains. There's a terrain type on Venus occupying about 7% of the planet's surface called tessera. Now, that's not a geological word. It was a word invented in the 80s to explain this particular terrain type on Venus. The point about tessera is that, and this is some of the work that I'm doing, I think the case could be made that they look a lot like old, ancient parts of continental interiors on Earth. Continents on Earth are made of a different kind of material to the basaltic plains that make up the seafloor or the plains on Venus. It has long been proposed by some that the tessera on Venus might actually, in fact, be like continents made of a slightly different kind of chemical rock type. Taking samples from the tessera is something that people since the 80s have proposed to do and have proposed to put landers there. The problem is there's a real challenge landing on the tessera because we know that they are rougher than the smooth plains where we know the Soviet landers touched down. That just means that it's a technical challenge, doesn't mean that it's not worth doing. If we could take samples from the tessera, multiple tessera, if we could take samples from multiple rock sites, and with this big ass balloon system floating around waiting to collect these samples over, say, 10 years, also taking a lot of in-depth sampling of the atmosphere at different times, day, there aren't really seasons, but certainly different parts of the Venus year, different altitudes, different latitudes and longitudes. That's the kind of data together that would really help advance our understanding of just how Venus ended up being the way it is.
But it also give us that insight into these exoplanets, because we will always have really imperfect information about these other planets out there. And we'll argue about this for possibly decades. I mean, this is like, I'm going to rant here now, my turn. But I sort of think about this question, and people are like, oh, we're finding all of these other Earths and we're trying to figure out whether or not there's life there. And obviously, yeah, if you saw chlorofluorocarbons and you saw some industrial pollutants, or if you saw, maybe there's some really clear signals, but probably it's all going to be, incomplete, and people are going to argue it's inconclusive, and people are going to argue about whether or not it is. Yeah. And that because you think about the arguments that have been had about both Mars and Venus. And if we can't figure out if there's life on Mars and Venus, it's going to be so hard to conclusively say that there's life on another world. And so the more we study, the more we understand Venus, the more we have this filter that we can then look again at the exoplanet worlds and get more definitive answers.
That's exactly it. And so what Venus is going to help us understand is how you get a planet to remain habitable. It won't necessarily tell us much about whether or not a world is inhabited, because really abiogenesis is the word we use to describe the creation or formation, creation by a creator or by stochastic processes in random nature, however you want to believe it. But it's the formation or the arising of life from non-life. It must have happened at least once on Earth. It probably happened a whole pile of times. But we don't understand it. We've never been able to replicate definitively life in the lab. So even if we understood that there might be dozens of Earth-like worlds that are blue, and in 1,000 years we have telescopes that interferometric telescopes the size of the solar system, and we're able to actually photograph the surface features of these things. And you and I are jars and heads in jars in Futurama, right? And we're able to see these data. That still won't necessarily tell us that they are inhabited, but it might tell us that, say, the outcome of Earth happens 1 chance in 4 for every large rocky world, and 3 chances in 4 it's a Venus, or something like that. Figuring out those odds is going to be one of the most important questions we can do, because it tells us whether or not Earth really is unique in the cosmos. Now, Earth is unique for all intents and purposes, because we are never going to visit these worlds. In fact, Venus is the only exoplanet Earth-like world we will ever likely get to, because the technical challenges involved in going to an exoplanetary system are formidable and far beyond us for the foreseeable future. So for all intents and purposes, it's Venus and Earth. But you're right, we are not, unless and until we see lights on the night side of a planet that we can definitively say are not, forest fires or something, although that would imply life, or some sort of methane release, although that would also, well, you can produce methane. Yeah. Short of, getting a transmission with some prime numbers or seeing a city on the night side, it's very hard to say we're going to ever find anything that's going to be unequivocally evidence of life. And certainly a technosignature would be easier to parse than a biosignature, because there's probably a lot of different ways you can get the same kind of biosignature. Let me just actually step to the side and say this. The idea of a runaway greenhouse effect holds that Venus at some point, if it were ever somehow clement, it just got terrible. If Venus had ever had liquid water oceans that were stable liquid water on the surface, and it began to lose them as the surface temperature increased by whatever mechanism was driving that runaway greenhouse, there is a short period, relatively speaking, of geological time when by that liquid water becomes steam up in the atmosphere, and then photo effects from the sun start to break that water apart into hydrogen and oxygen. And for we think, relatively short period of time, the atmosphere becomes enriched in oxygen. And one of the things we think might be a powerful, prominent biosignature is looking for free oxygen in a planet's atmosphere, because it's kind of weird to have so much free oxygen that hasn't just bonded and oxidized stuff, as Earth does. So if you found oxygen in an atmosphere that was not bonded, but it was just basically molecular oxygen, on the one hand, one possibility is that somehow something like archaea, bacteria, are producing it. Or that planet's in the midst of a runaway greenhouse effect and it's sterilizing itself. Right. So even that signature is equivocal when you see
so it would sure be nice to know which it is. Well, Paul, it's been a pleasure to talk to you. And as I said, you specifically have been a factor in my current obsession with Venus. And so thank you. I mean, Venus can thank you for its day of execution. But
I do what I can. I do what I can to spread the good word, to evangelize.
But if people want to keep track of your work, and what is the best place to do that?
Best place, find me on Twitter, or it's a dumpster fire. It's amazing to see how it's falling apart, but I'm still there and I'll be there.
I hope you replicate that feed over on Mastodon too, because it's
I'm going to try. Yeah. Right now, I spend, because to me, Twitter is like a kind of a fun side thing to do, and I have so many other things that I'm always doing. I may get to Mastodon eventually. Yeah. For the time being, at the Planetary Guy, you will find me shit talking Mars and talking up Venus is a place to explore, and anything else that comes across my desk that I think.
Wonderful. All right. Well, when we do get funding for the Venus sample return mission, would you come back and talk about what you found?
You bet I will, because I'll probably be going door to door to try and raise money for it.
That sounds good. All right. Thanks, Paul. Good luck.
Thanks, Fraser.
You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There, you can find an audio version of all of our news, interviews and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps our ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Jay Dennis, David Giltonen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.